Hi, Martha again. I think I know what's happening.
Flip here.
Bit here.
Hello, I'm Octavius. Next stop, neural networks. Hello, world. Sorry, wasn't ready yet. Okay, come in. Hi, I'm Octavius. Let's start with the basics, shall we? Whoa, yes, please. Neural networks are made up of simple building blocks, and the simplest is the neuron. Oh, hi, Flip. Hi, Bit.
Yo.
Hey, Doc.
Just like their biological namesake, these neurons accept multiple inputs and combine them to produce outputs. Nearly anything, as long as you can measure it numerically.
Think of your inputs as like properties in a spreadsheet.
But kicked on its side.
Not strictly necessary, it just looks better going left to right.
This is where it starts, our first layer of inputs. Our goal then is to use the values generated by that input layer, no matter how complex, to generate an output layer on the other end with a nice simple answer. And that's it. Any questions? But what happens in between? Exactly. Those hidden layers in between are performing a simple classification task, but across a complex, multidimensional data set. Each feature's numeric value, x, is simply added up in the neuron.
And that sum helps determine the slope of the line.
But some features deserve more weight than others, so first those inputs are adjusted up or down in strength. Oh, so the weights are one of our dials. Yep. Another is the bias, an offset to the whole sum that's also adjustable by weight. So, adjusting weight adjusts slope, and adjusting bias adjusts the y-intercept? Just so.
Told you she was a fast learner.
Then we squash that linear classifier into a nonlinear form, like a sigmoid function. This activation function puts it all in a manageable range, like 0 to 1 or 1 to -1, and allows for smooth adjustments in the learning process. Huh! Here it is, fully unpacked. Yikes! But for simplicity's sake, let's just combine sum, bias, and activation function into one node, and use line thickness to indicate weights. Whoa, yeah, let's! And now the output of that node. Oh! Can be the input for another. Just so. And another, and another. Whoa! So when we train neural networks using backpropagation and gradient descent, that process adjusts those weights and biases? Yup. We call those automated adjustments model training.
Look, Ma, no hands.
That's cool, but where do we engineers come in?
Oh, all over. Engineers choose the right architecture, tweak the number of layers or nodes, select activation functions, all kinds of decisions.
No.
We call that stuff hyperparameter tuning.
Information has structure. A well-trained neural network can help you navigate that structure. That's what you're doing when you draw those regression and classification lines. Easy to do by hand when there are only one or two features. Oh, look at him go! But with multiple features come multiple inputs, and that means multiple dimensions to navigate, which makes drawing a simple, straight boundary between A and B seem next to impossible. What? Luckily, our digital cousins see other dimensions mathematically and can find us paths through that structure.
Oh yeah, piece of cake. Just gotta bend the underlying topography. For example, it seems like no straight line could separate these two shapes, but neural networks find a way.
This is where those hidden layers shine.
They transform data. They stretch and squish space, but never cut, break, or fold it in pursuit of an answer.
It's like drawing a straight line between Antarctica and the other continents. Might seem impossible on a globe, but not so with a little change of perspective. If each neuron contains a different linear function, combining them gets us more complex shapes for data fitting. Ooh, so with enough neurons I could fit any dataset no matter how complex? Wahaha! Not so fast. Too many neurons may lead to overfitting.
Not to mention inefficiency. Here's your latest energy bill.
Accuracy ain't the only marker of a good network.
Say, why do we call them hidden layers?
Hoo boy, good question.
Well, we know what features go in, we know what answers come out.
And we can even describe how hidden layers work.
But in a fully connected neural network, each node blends results from every node on the previous layer. Who's to say what features it's even looking at?
As data scientist Cassie Kozyrkov puts it, we're automating the ineffable.
Now, a fully connected neural network is just one kind of architecture. Nice hat! Thanks. Let's ride to another popular stop on the neural network map. This whole field is in flux, forever under construction. Some of today's most popular destinations were just prototypes 10 years ago. Recurrent neural networks, such as LSTMs, loop back on themselves repeatedly, addressing problems with the temporal element, such as speech recognition. Others, like autoencoders, helped make sense of unsupervised data, reducing the dimensionality of overflowing big data. The network we are heading for has been especially popular for analyzing. Hey, who are they? Oh, that's the Jan line. None of those passengers exist. Don't make eye contact. Here we are, all out for convolutional neural networks. Aha! I've heard of these!
They get a lot of press. Oh, I love this one. She really captured the 110011011010, don't you think?
Images are all just grids of numbers to a CNN. Well, isn't that true of any neural network that handles images? Sure, but CNNs offer a unique method for parsing and obtaining all that image-based data.
Including any data type that can be represented as images.
Even a low-resolution image like this contains a wealth of information. Every one of those 1024 pixels is a separate input. 3, in fact, if you count the red, green, and blue channels.
It's Uncle Rufus!
Talk about a multi-dimensional input layer, and that's not even high-res or video.
Getting flashbacks here.
We might still want a simple, one-dimensional yes or no when we're done, but it has to work for any cat at any angle and in any portion of that image.
Whoa, a tall order!
Indeed, and CNNs fill that order by breaking down those huge matrices of pixel data into manageable chunks layer by layer.
Let's start by building a map of cat-related features in our source image, catch.
What's this?
A filter. It starts out as a matrix of random weights, but the algorithm tunes it. A convolution involves moving this filter across the entire image by a variable interval known as a stride.
Oh, it's multiplying the source data by that matrix.
The result is called a feature map.
These feature maps go through pooling to further reduce their computational size.
Ooh, so you can keep stacking them to hunt down more features.
In their earliest stages, filters may detect no more than edges and orientation.
Fun fact, your brain's visual cortex initiates detection this way too. In fact, it was an early inspiration for CNNs.
But with every subsequent layer, composite features start to emerge from the noise. See? Me.
So it goes from lines and angles, through whiskers, paws and fur, and then finally to cats or dogs.
Well, yes, no, and yes. We may never know exactly what features it sees in the middle, but whatever they are, it can find them no matter where they're hiding.
CNNs aren't fully connected like our first example, but the final output layer is connecting to all the neurons on the previous layer.
This classification layer delivers the accurate answers we all...
Gang?
Oh, what's this? Were there no Rhying robots in the training data?
Well, there should have been.
Nope. Only to the walking variety. Classic selection bias.
Well, that's not fair. Expecting all robots to walk.
You can't take the sky from me.
Guess I always thought of data as being unbiased, just numbers and all.
Datasets are products of the time and place they're assembled. Even if you proactively try to create neutral data, the people doing the compiling may have their own implicit biases.
This is more complicated than I thought.
We might be dealing with something called latent bias, too. Take a look at these basketball photos and see what they all have in common. See anything familiar?
I don't know, just looks like a bunch of arms holding... Oh!
Engineers and ethicists are still coming to grips with how neural networks see the world and the roles we see for them in the coming years. By simply turning a CNN upside down, researchers took a peerless image classifier and gave birth to generative adversarial networks, or GANs, which can generate beautiful surreal images, but also those notorious deep fakes.
Yeah, I want to be part of the solution, not part of the problem. I just hope I can tell the difference when the time comes.
Hey, just learning how it all works is a great place to start.
Here!
Here.
Well, look out, world, because I'm 99% certain I can.
Hey, Martha! Ooh, where am I? What's that? Who are these guys?
This is...
Actually, I don't care. I need you on deck in like 10 minutes to present to the shareholders.
Is he always like this?
Yep.
Okay, thanks. Whee!
Oh dear, that was a lot of info we just...
I'll go sabotage the meeting room to buy some time.
I knew I should have gone slower. They're going to laugh me out of the Cephalopod Teaching Academy.
No. I've got this.
Now it's your turn. Continue your journey into the world of machine learning.